Oh, great.
You can move again.
Up and down. Okay, good. Thanks.
Okay. So good morning, everyone, and welcome to this second session of the day. The first talk will be given by Petros Maragos, who is professor in the National Technical University of Athens, and I am extremely happy to be Petros with us in the room because, as you will see during his lecture, Petros Maragos is probably the major figure on the intersection of the three topics I was using for the session of today: tropical geometry, max plus algebra, mathematical morphology, and the interaction of everything in machine learning. So let's just enjoy the talk by Petros.
Thank you very much. Thank you for the invitation. I'm very glad to be here with all of you in this enchanted place. I remember 19 years ago, there was the Mathematical Morphology Symposium here at the College of Mean. Well, today the topic is a combination of tropical geometry and machine learning. Actually, tropical geometry is a tool for machine learning. Tropical geometry is emerging recently in computer science. It's a combination of algebraic geometry and polyhedral geometry. And it's becoming actually a nice collection of ideas and tools for understanding, designing, analyzing, and understanding many classes of both classical and deep machine learning. And this will be the topic of my talk. Well, what does a tropical adjective mean? It was coined by French mathematicians Dominique Perrin and Jean-Éric Pin to honor their Brazilian colleague Imre Simon, who was pioneering in mean plus algebra as applied, though, to computer science, not machine learning, finite automata in machine learning. In our exposition, we understand tropical in the following way, by using the Greek word tropi or tropikos, which means turn around. So actually, many of the curves and surfaces in tropical geometry, as you will see, they have this polygonal form. They turn around. So the word tropical here acquires a more substantial meaning. I will start with a very brief synopsis of tools and objects from tropical geometry, and even less from max plus algebra. Then I will use that for the main part of the talk, which is, as I said before, understanding, analyzing, and sometimes designing neural networks of three kinds, or machine learning systems of three kinds: neural networks with piecewise linear activations, neural networks whose activations are nonlinear, like the max plus formulation for mathematical morphology, and piecewise linear regression, and some applications to neural network compression. Here are my collaborators for the topics covered in this talk, mainly PhD students and master thesis students. Well, according to McLagan and Sternfels, tropical geometry is a marriage between algebraic geometry and polyhedral geometry. In our view, tropical geometry is a dequantized version of Euclidean geometry and analytic geometry, where the word dequantized will become clear in a few slides. A few references. Actually, talking about the references, let me mention the following thing that I skipped. I gave recently a tutorial talk at the international conference ICASP in Seoul, the same topic. And in this link, you can find these slides plus many more and more topics covered under tropical geometry for machine learning and optimization. Well, a few references. There are a few books on tropical geometry like McLagan, Sterfels, Edinburgh, Mikalkin, and Susting, and Joswick. But also there are some classic, and also the book by Cunningham and Green on minimax algebra. But also there are many classic papers related to the subject. For example, on tropical convexity, including the work of Stefan Gobert and his collaborators from the Max Plus group. Stefan is with us today. Now, applications of tropical geometry machine learning, again, some references. One of the first references was the work by Pachter and Sternfels on using tropical geometry concepts to analyze statistical models of machine learning, specifically the some types of hidden Markov models. Then our work started using tropical geometry to understand neural networks with piecewise linear activations in parallel to the work of Zhang, Naitsat, and Lin. And we continued with the topics that you will hear today. Plus, there are many more references in this tutorial that I mentioned before. So for those members of the audience that are not familiar with tropical mathematics, just a few quick definitions and mentions. We have the two tropical semi-rings, the Rmax. Symbols are missing, yeah. Symbols are missing. Okay, well, let me go on. What is missing here is the symbol R, Rmax, and Rmin. To save time, if that's the only thing missing, I will continue. So we replace the traditional real addition with max or min, and the traditional multiplication we replace with addition. So this is called max plus and min plus. They are dual. So these are two tropical semi-rings, and if we, let's say, take some classic Euclidean curves, like all the green ones are the traditional Euclidean curves, like the line, the parabola, the cubic curves of Euclidean polynomials, and we replace the addition with max and the multiplications with plus. Then we obtain the max plus tropical polynomials that you see in blue. And as you see, their curves are polygonal lines that bend around corner points, and the number of corner points is related to the degree of the polynomial. These are the simplest objects of tropical geometry, and you can compare between the middle column and the right column. You can compare the duality between using max plus and min plus tropical polynomials. The max plus are convex, the min plus are concave. Another tropical object of interest is the so-called tropical curve of a tropical polynomial. It's the analogous of the zero locus of a classical polynomial. So the tropical curve, let's say, of a tropical polynomial is a set of points at which the maximum or minimum is attained by more than one of the monomial terms. And you see an example here on the left of a max tropical polynomial, a two-dimensional one. You see in black the tropical curve. And on the right, you see the same type of object, but for the mean plus, the dual, the mean plus tropical polynomial. Okay, another object of great interest in our discussion is the Newton polytope of a tropical polynomial, which is the convex hull of its coefficient vectors. You see an example here of a two-dimensional tropical polynomial. So you see this convex hull, which is the Newton polytope. I'll come back to this. And there's a duality between the Newton polytope of a tropical polynomial and its the corresponding tropical curve. You see the duality here for an example of a two-dimensional tropical polynomial. Now, going to tropical polynomials of degree 2 in two variables. We have this classic conic, and then its tropical version, where, as I said before, the easy rule, the easy trick is to take all additions between the monomials and turn them into max or mean, and then turn the multiplications into additions. And then you create this tropical polynomial. We will see that in a more systematic way called dequantization. And you see the underneath, you see the graph, the tent of this two-dimensional second degree mean plus polynomial, and underneath the tropical curve, where the minimum is attained by more than one terms. Okay, so we have seen mini polynomials of degree 1 in two variables of degree 2. They are tropical curves. Two tropical lines on the right on the plane intersect at one point. Below, you see an example of a cubic tropical curve, and so on. Let us now see this concept of dequantization developed by Maslow and his collaborators in the field called idempotent mathematics. For us, it's something known in convex analysis called log sum exponentiation. It's an approximation to obtain the max or the mean of two numbers using smooth functions, and therefore differentiable later on if one needs differentiation. So you take, let's say, the two numbers A and B, the two real numbers. You scale them by a temperature parameter, tau. You take you exponentiate them, take their sum, and take the log, scale them again, and let the temperature go to 0. And this way you obtain the max. By negating the temperature, you obtain the mean. And below you see several examples of smooth, smooth functions and the effect of temperature, where by letting the temperature go to 0, you obtain the dequantized version, the blue one, which is a tropical polynomial. So this is the concept of dequantization or tropicalization, and it is used extensively by Maslow and their colleagues, and also other groups in going from classical, let's say, smooth functions to these tropical functions. So the rule then is to have a classic polynomial, or more specifically a polynomial, where we impose positivity in the constant ck multiplying the monomial. We we allow, in contrast to McLeod and Sternfels, we allow real coefficients, not just integer coefficients. We allow integer coefficients, real coefficients, AK. And then we use sort of this concept of Viro's logarithmic paper, or equivalent to this log sum exponentiation, to take the log of every monomial, which turns this multiplicative constant CK turns it into an additive bias term, BK, and the monomial essentially becomes a linear form. And the final result is to obtain the tropical polynomial, which is essentially a piecewise linear function. The vector AK is the slope vector in multiple dimensions, and the BK is the bias. Or some people may call it a max-affine function. So these are the tropical polynomials in general. Now, by using again these symbols that are missing, it's the symbol bold R. Okay, so by using, let's say, tropical polynomials, one can create tropical half spaces. You see some examples here in 2 dimensions on the plane. On the left, you see, let's say, a tropical line separating the plane into 2 regions, and then several tropical lines whose creating lots of pairs of tropical half spaces, and their intersection creates polytopes. So then polyhedra can be formed from finite intersections of these tropical half spaces, where these tropical half spaces correspond to inequalities where on both sides you have a max plus polynomial. And then the polytopes are compact polyhedra. And similarly, in 3 dimensions, you know, this you have 2-dimensional max plus or min plus polynomial, like this F polynomial and the G polynomial, separating the 3-dimensional space into 2 regions, and intersecting some of these half spaces creates these compact polytopes, which in machine learning will represent for us decision regions. So if we have a machine learning problem, then these polytopes will contain the positive examples of certain classes, or the negative examples of certain classes. So this is the link between these polytopes and machine learning. The Newton polytopes now are more useful if we extend them by 1 dimension. We take the slope vector, AI, and we concatenate it with a bias vector. So we increase the dimensions by 1. And this is called the extended Newton polytope. Again, the convex hull of these extended vectors. And there is a very useful result that says the max plus polynomials with the same vertices in the upper hull of the extended Newton polytopes correspond to the same function. Examples. We see in blue the standard Newton polytope of this max plus polynomial in 1 variable on the left. In green, you see the extended version, the extended Newton polytope, and same idea with an example in 2 dimensions on the right. So it is the extended Newton polytopes that are more useful for us. For example, we don't care about terms in this max plus tropical polynomial whose vertices are below the upper hull, because they will be subsumed by the max function. So we care only about the vertices on the upper hull. This defines uniquely the max plus polynomial. Now, what can we do with these Newton polytopes? At least two types of algebraic operations corresponding to geometric operations between the Newton polytopes. If we have two tropical polynomials, P1 and P2, if we max them, here on the left, you see actually the Newton polytopes in blue for the P1 and P2 polynomials on the left. Sorry, is this working?
You have the mouse.
Okay, I have a mouse. I have the mouse. Okay, so on the left, you see the Newton polytopes of two max plus polynomials, P1 and P2. Then if we max them and create a new polynomial, P1 max P2, then the result will be the corresponding Newton polytope will be the convex hull of the union of the two Newton polytopes. And more useful for us will be the second operation if we sum. Why sum? Because neural networks, we sum the results, the outputs of several nodes, and every node, let's say, will correspond to a Newton polytope. So we sum the outputs. What happens to the Newton polytope? Well, summing the two polynomials corresponds to taking the Minkowski addition, the Minkowski sum of the Newton polytopes, and you see the result on the right. The middle one is the green one is the Newton polytope for maxing the two polynomials. The right one, the brown, corresponds to the Newton polytope of their sum. So this was a very quick synopsis of some of the main concepts and objects from tropical geometry that we'll be using. Now, I will make an even a briefer synopsis of some things from Max Plus algebra because many of you here are very familiar with it. Well, Max Plus algebra has become, a valuable, a valuable mathematical background for several fields. Scheduling and operations research in minimax algebra. Of course, in image processing and computer vision, we have mathematical morphology. In control optimization, we have max plus control, max plus linear systems, optimization on semi-modules, and actually in both areas, the application of max plus algebra to image processing, computer vision, and the application to control and optimization. In the audience, actually, we have several colleagues who have been very active. In image processing, we have Jesus Angulo and people from mathematical morphology. In control optimization, we have Stefan Gobert and his group. Another area which is very important in machine learning and has benefited from tropical algebra is speech recognition. Actually, the Caldi software that essentially improved speech recognition based on hidden Markov models was based on tropical algebra, on using actually the min plus semi-ring. Another area which is less well known is the probabilistic graphical models with the max sum and the max product algorithms. And then we have also mathematical physics. For example, the group by Maslov, Litvinov, and their colleagues in adipondent mathematics, plus the convex analysis optimization areas. As I said before, linear algebra versus max plus algebra. We have these fundamental replacements of classical addition by max, classical multiplication by addition. The max plus is commutative, associative. Max is commutative, associative, distributive over addition, but inverse. The only thing that's missing, I'll come back to this. Now, I will be using some notation. That's why I'm essentially summarizing the slides. We'll be using some notation. So we'll be using this notation for pointwise max between vectors. As vectors will be in lower boldface. Matrices will be in capital boldface. So this notation essentially is pointwise max between vectors or matrices. We have, instead of having multiplication by scalars, we have addition of vector or matrices by scale with scalars. And then the kind of new notation I'm using is the matrix max plus matrix multiplication, using this box with a plus in it. Instead of taking the sum of products between, let's say, a row from the first matrix and a column from the second matrix, we take the max of sums. And then the same symbol, the box plus symbol with a prime, is the min plus matrix multiplication. So these are the two, these are only the two kind of strange symbols I will be using. I should say that in this area of tropical mathematics, one disadvantage that I consider is the notation. Okay, it's not established yet. Now, there are two views in these nonlinear of these nonlinear operations and the spaces created by them. There is this view of semi-rings, where we have the max plus semi-ring. Max plus, we have two operations. The first operation, the max, is only idempotent semi-group. The second one is a group, the addition. Same thing with a min plus, and they are dual between them. Another view of them is a lattice. Well, the lattice, a flat lattice, where we have the extended set of real numbers equipped with max and min, which contains both semi-groups. Okay, and if we add, let's say, the addition, then we obtain something that can be called weighted lattice. So I guess in my presentation, I kind of prefer this second view of the operations involved, the weighted lattice. I think it's more compact. It contains both of them, and it leads us to something useful for the algorithms to come, something called adjunctions or residuations. In the same way that we have the classical concept of a linear space, now we can talk about a tropical space, which is actually on weighted lattices, where instead of having, let's say, a system, an operator, where if its input is a linear combination of functions and the output is the corresponding linear combination of the output functions, now for a tropical space, we have a maximum of a max combination of functions with additive constants, creating in the output a corresponding max plus combination. One of the advantages of working with lattices is this classic concept developed by Serra and Materon, and then later by Harsmans and Roms in mathematical morphology, of these four types of operators. The dilation operator is anything that distributes over supremum, max. Erosion, any operator distributing over infimum. The opening now, it's any operator that is increasing, adjoint extensive and idempotent, whereas closing is increasing, extensive, and idempotent. And then a fundamental concept is that of the adjunction or Galois connection, which tells us that dilation and erosion can come in pairs. So let's say a delta epsilon adjunction, where a delta is a dilation, epsilon is an erosion. They come in pairs if and only if they satisfy this double inequality. And if they do that, then we have as a, as a very useful byproduct, we have projections, we have filters by cascading dilations and erosions. And a few examples very quickly, because I guess these are known to most of you. From set operators, we have dilation of sets, which is the Minkowski addition, erosion of sets, which is the Minkowski subtraction. If you cascade the two of them, you obtain an opening of a shape or the closing of a shape, which are kind of smooth, nonlinear filters. This idea extends to images, gray images, in the form of max plus convolutions. So the dilation of a function f by function g is a max plus convolution, whereas the erosion of f by g, again, a symbol here shows in a crazy form. Supposed to, this symbol that is a dollar sign in my PowerPoint, it was supposed to be a circle and a minus sign. Okay, it's a mean plus correlation, but they're in a form that if you cascade the two of them, you obtain idempotent operators. You obtain, let's say, filterings, projections of the original gray image into something that is smoother, but it has a better preservation of its edges than, let's say, linear smoothing filters that are used in computer vision, like Gaussians. So this idea of using always pairs between dilation and erosions is one of the benefits of working with lattice operators on lattices. So we have seen, let's say, these two types of adjunctions: the set adjunction of Minkowski addition, Minkowski subtraction, and then the adjunction of max plus convolution and min plus correlation. And now, in the machine learning, we have a new adjunction that is the max plus product of a matrix A with a vector X, and the min plus product of a matrix A star with vector Y. And if we formulate them correctly, then these vector operations actually become adjunctions. Now, in applied mathematics, actually, before I go into this, I would like to show this geometric intuition of using the adjunctions for solving a fundamental problem in max plus algebra, which is very useful in machine learning, using these tropical functions. Okay, how do we solve the traditional problem of linear algebra? Ax equals b. In our case, A times X will be the max plus matrix product. So given A and B, how do we find X? Okay. Well, there's a theorem by Cunningham and Green that says that the greatest solution, if it exists, is obtained by using the min plus product of the data vector B with the adjoint matrix A. It has linear complexity, whereas the traditional linear algebra, solving it has cubic complexity in general. The geometric intuition here is interesting, that this min plus product of A star with B, it's a vector erosion, and then the max plus product of this with A, it's a vector dilation. So the result, it's an opening, it's a projection, and it gives us the greatest subsolution, the greatest solution that does not exceed our data B. So from this point of view, then, dilation and erosion, these adjunction pairs, give us a geometric intuition behind solving these problems. And in applied mathematics, the same idea exists in residuation theory, where we want to solve, let's say, a problem psi of x equals y, but there's no inverse to psi operator. But if psi is an increasing operator, we can come up with a so-called residual operator, this psi sharp. And the cascade of them will give us the greatest sub-solution to the problem. Well, the ideas actually are one-to-one equivalent in the following way, that the adjunction is equivalent to residuation if and only if the psi operator is identified with the dilation and the residual psi sharp is identified with the erosion. The advantage of calling them dilation and erosion is, as I said before, the geometric intuition provided by dilation and erosion from their application to image analysis or shape analysis. I will just mention by titles only, because this is not the topic of the talk. Earlier spatial cases of Max Plus algebra and applications. Only by title. I will not go into that because this is not the topic of the talk. Well, in the same way that we have linear dynamical systems, we have now Max Plus dynamical systems. They have been applied in automated manufacturing. They have been applied in dynamic programming, finding longest and shortest paths. They have been applied in speech recognition, these weighted finite state transducers used in the Caldi software system. Actually is based on these Max Plus systems, and these transducers that provide speech recognition and language recognition using hidden Markov models. They are 100% based on them. In computer vision, distance transforms are essentially obtained by using a recursive mean plus difference equations. In computer vision, scale is important. Multi-scale analysis is very important. The most well-known multi-scale analysis computer vision is modeled in a continuous form by the heat equation. So, for example, if you have let's say an original image, and then you want to create its multi-scale Gaussian convolutions, then this heat partial differential equation is what exactly models this and gives you this continuum of multi-scale Gaussian convolutions of the image. And now, if we do this dequantization process, where we take this H parameter from the Gaussian PDE, the heat PDE, and introduce a new parameter U equals e to the minus W divided by H, and consider Hopf's PDE. Using dequantization, we end up with the Hamilton-Jacobi equation, which actually models multi-scale erosions by parabolas. And you see one example here. So what I'm trying to say is that this transition from a classical linear equations, either in polynomial form or in differential form, using a dequantized way, brings us back to these nonlinear functions, the tropical functions, or these nonlinear convolutions used in computer vision. Now, the first class of neural nets that has essentially attracted the attention of tropical mathematics is neural nets with piecewise linear activations. Examples include the ReLU, the rectified linear unit, where the activation is the simple function max of 0 and v, or the leaky ReLU, where we have maximum of alpha v comma v, where alpha is a very small constant, less than 1. And V actually is the linear combination of the inputs to the neural nets. We have X being the vector of inputs to the neural net, to this perceptron. B is the bias, and W is the vector of weights. A more general type of neural net activation is the max out unit. We have a maximum of several of these forms. So this max out unit can be parallelized with, let's say, a max affine function. So it's a max plus polynomial, essentially. Well, an interesting fact about this type of neural nets is that it's about their linear regions. Linear regions are defined as the maximally connected regions of input space on which the neural net output is linear. This is a concept by Montufar 10 years ago. A very important concept. The idea here is that the claim is that if we have more linear regions, then we have more expressive power. Of course, this argument is not foolproof because we may have sensitivity or we may have more linear regions that are very small and noisy. But some researchers use that as I said before, as an expressive power of the neural net. You see how the input space is subdivided into convex polytopes. Each of them is a linear region at layer 0, the neural net, layer 1, layer 2, and so on. Okay. Well, one useful result for a single neuron is the following proposition, that the number of linear regions for a single max out unit, again, a max out unit is for us a max plus polynomial, is equal to the number of vertices on the upper half of the Newton polytope. So that's where now the geometry comes in, where the Newton polytope with its upper hull essentially controls the number of linear regions. All the other terms that correspond to interior vertices can be removed because they do not affect the function of the neuron of this neuron. An example here of a neuron with two inputs, x1 and x2. So you have this neuron, which is this max plus polynomial in two variables. And you see the upper half of its Newton polytope, it has 6 vertices, and these 6 vertices correspond exactly to the 6 important terms that make up and define uniquely this the output of the neuron. Now, what happens if we have a collection of tropical polynomials? Then we can work with the Minkowski sum. Another useful proposition here, the number of linear regions of an area that has n inputs and m neurons, it's upper bounded by the number of vertices in the upper convex hull of the polytope that results by the Minkowski sum of the individual Newton polytopes. Okay. If each one of these P1 and P2, PM, let's say, are very simple neuron functions, for example, consisting of one term and 0, then their Newton polytope, it's one line segment. So the Minkowski sum here will become a zonotope. It's perhaps the easiest geometric form of a polytope, the zonotope. Okay, now, again, in the algebra of polytopes, or the algebraic geometry of polytopes, it's very important to bound, let's say, the number of vertices and faces, and So there is this result, which is an upper bound, though. It concerns the number of linear regions of neural nets that have n inputs, m outputs, layers, and consisting of convex piecewise linear activations of rank k. Rank k means that every activation has k terms in the max plus function. And then in the case of ReLU, when we don't have max out units, the upper bound becomes simpler. But it's it's a research field to count in practice, given a network to count the number of linear regions exactly or approximately. There are several exact approaches which become impractical when the problem involves too many neurons. There is this mixed integer programming approach by Sarah and his group, but they assume bounded range of input space. In our recent work, we have come up with a randomized geometric algorithm to sample the extreme points of the upper half of a polytope. And there are also works in other fields, let's say in the field of computational geometry. There are other works that deal with similar problems, although not motivated by machine learning. In conclusion, these are some theoretical results that will be useful later on. Any continuous piecewise linear function is equal to the difference of two max polynomials. As I mentioned before, the essential terms of a tropical polynomial are in bijection one-to-one with the vertices of the upper half of the extended neural polytope, and a neural network with a ReLU type of activations of any depth can be represented as a difference of two max plus polynomials. So essentially, this is called a tropical rational function. Tropical rational function is a difference of two max plus polynomials. And then there is work by Calafiori and Stéphane Gobert using the Maslow quantization to design universal approximators for convex or log-log convex data, essentially replacing the piecewise linear approximation to a convex function f, replacing it with a smooth version that comes from this concept of dequantization with a parameter t, a temperature parameter t. Moving on now to the second class of neural networks that can benefit from these ideas. These are more traditional networks, morphological networks, as the word implies. Their nodes are essentially morphological operations. What's the motivation? Well, the multiply accumulate, meaning the linear operation of the perceptron, it's still ubiquitous. Two questions that we raise are the following. Are the linear inner products and convolutions the only biologically plausible model for neural computation? Can we use the results from nonlinear mathematics to reason about the complexity and dimension of learning models and so on? Here is the classic Rosenblatt's perceptron introduced in 1943. Uses a linear combination of the inputs and it passes them through a soft differentiable nonlinearity sigma, like the sigmoid. The morphological or max plus perceptron does not use an activation function. It simply uses a nonlinear combination of the inputs. Instead of using a linear combination, it uses a max plus combination. The unknowns here to be found are the weights W. Or we can use a dual perceptron, which is an erosion, a min plus. Ritter and Ursit in 20 years ago, they argued actually in a nice paper about the biological plausibility of this max plus perceptron. Obviously, it's related to a max out unit. I mean, it's a special case of a max out unit. Well, one result that we have shown is the following, that if we have a pattern classification problem, where all the pattern vectors X, they form a matrix, a capital X, and this capital X matrix can be divided into the positive and the negative patterns, which correspond to the two classes. The C1 class is the positive class, the C0 consists of the negative vectors. Then if we are to separate them with a max plus perceptron, then we're looking to find a tropical polyhedron, actually. We're looking to find a vector W so that the tropical polyhedron formed by the corresponding tropical half spaces completely separates the positive from the negative examples. This is possible if this separability condition is satisfied. And this separability condition is nothing else but an application of solving this system of max plus equations that I mentioned before using this adjunction. So this is an application of this adjunction. The adjunction here is a max plus matrix product of the matrix of the positive vectors with the vector formed by the mean plus the adjoined mean plus matrix of negative vectors and the zero vector. Well, if this vector now is non-negative, then we have a fully separable problem. But of course, this is a theoretical, concept to have a completely separate problem in life. So in practice, we have to deal with non-separability. And in morphological neural nets, actually, there is a rich literature. Here, I'm just sampling a few names. More references can be found in this tutorial that I mentioned before. Some recent approaches includes something called convex-concave programming that I will explain in a minute. The reduced dilation erosion perceptron by Marcos Vale. Actually, Vale, I think, is here. And he will be giving a talk. Dense morphological networks, deep morphological networks, and something, a sparse approach to this. So the convex concave approach, what we have done here is we took a result that says essentially a max plus perceptron can be stated as a difference of convex optimization procedure, but implemented in a disciplined way. This disciplined way is part of a convex optimization Python language package by Sen and others at Stanford. We have formulated the problem in a similar way as in support vector machines. So we have defined a function to minimize that is the sum of the max of slack variables xi k and 0. These xi k slack variables are positive only if there is a misclassification. And our contribution in that was this formulation plus a weighted version of that, where we multiplied these misclassifications by weights nu k that are inversely proportional of the distance between the misclassified pattern and the centroid of the class. So we call that the weighted disciplined convex concave programming. For small data sets that you see here on the left, we have seen a clear improvement of using this for training the morphological perceptron versus training it with standard stochastic gradient descent. And on the right, actually, you see how the weighting improves. The weighting here is called regularization. The dotted separation curve is without regularization. The dash version is with regularization. It certainly improves the result. So for small data sets, I think it's worthwhile to explore this convex concave programming approach to designing neural nets for small data sets. For large data sets, we have found that this convex concave programming, it's time consuming. So we resorted to stochastic gradient descent for large data sets. And we used a convex combination of a dilation perceptron and an erosion perceptron. So we attempted to train them using this convex concave. It is possible, and I think it's an interesting future objective to analyze. But again, we experienced that the time it takes is much longer than stochastic gradient descent. So we trained them a dense morphological neural net on the larger data sets, the NIST data sets, and the fashion NIST, and we focused on sparsity, okay, by using the baseline approach, the L1. So when the weight vector had an L1 norm that was below a threshold, we pruned it. We took away this neuron. This is called the structured way of pruning, of compressing the neural net. The experiments we did were with dense neural nets, where we had either in the hidden layer, we had like 400 dilation perceptrons, or 400 erosion perceptrons, or 200 dilation and 200 erosion perceptrons. We compared them with traditional neural nets that used feed-forward, the feed-forward architecture, and used ReLU activations. Now, the results are very encouraging. For example, the green on the left here, you see the percentage of pruning. And sometimes the percent of pruning is very dramatic. It goes down to 1%. We keep only 1% of the nodes. And still, when we use, let's say, the dilation perceptrons, the green, as you see here, shows almost no loss of accuracy. Whereas the shades of pink, they show losses of accuracy for the neural network involved in the corresponding column. So the result here was that these nonlinear perceptrons, either dilation or erosion, or their convex combination, they showed resistance in the pruning, much greater resistance in pruning them without losing accuracy or much of accuracy, corresponding to compared to the traditional neural nets for these traditional databases like NIST and fashion NIST. And here are some images that may throw some light into why this happened. We trained them both using stochastic gradient descent as well as Adam. And we found out that if you compare the left column with the right column, you see that when you train these morphological perceptrons, very few nodes are active. So then it makes sense to prune severely. Whereas if you train traditional neural nets, many nodes are active. So you cannot really prune without losing significantly the accuracy. And between stochastic gradient descent and Adam, it turns out that stochastic gradient descent is better for pruning, but slower than Adam. Now, another approach, again, that uses tropical geometry for compressing neural nets is a method we developed called tropical division. I will be very, very quick on that for the interest of time. The idea is we have the original network polytope representing the original network, and we want to approximate it with a simpler polytope. That's the idea. Okay. And we want to accomplish that using, again, here's a brief reminder that if we max two max plus functions, the f and g, this corresponds to taking the convex hull of the union of their Newton polytopes. Whereas if we sum them, we take the Minkowski sum of their Newton polytopes. Okay, just a reminder. And here you see a few geometric examples. You see two functions, f and g, of two variables, and they are extended Newton polytopes on the left. On the right, the two examples, so respectively, the Newton polytope of their max, like a pyramid, and then the Newton polytope of their sum. Well, this concept of tropic division, okay? Well, we want to divide the polynomial p of x by a divisor polynomial d of x, okay? And if we interpret that in tropical terms, again, multiplication becomes max, and addition becomes max, and multiplication becomes sum. So then, in tropical terms, the tropic division means to find a quotient polynomial q of x and a remainder polynomial r of x, so that the original polynomial p is equal to the max of the sum between the divisor d and the quotient q and r, the remainder. Okay, but the above is not always feasible in a non-trivial way. So the approximate division we have come up with is the following. We impose this inequality that the result of this division should be below p of x, but in the largest possible way. So we demand that the quotient and the remainder polynomials to be found satisfy the above inequality maximally. Okay. How do we find this this quotient polynomial? Well, very quickly, the quotient polynomial will be a max plus polynomial that will be a max of these affine terms. They have a slope vector c and a bias qc. We try, let's say, out of a set of possible slope vector c, for each one of them, we try to push the divisor polynomial up so that it always stays below the upper hull of the extended Newton polytope of the original polynomial p of x, and the maximum height qc is the bias term. And then the terms that are not covered by these horizontal shifts are the remainder polynomial. Simple example to illustrate this this algorithm. The original polynomial p of x has a Newton polytope that is this green with this green upper hull. Okay, d of x is the red, and then out of this tropic division, the quotient is this blue curve, and the sum of the quotient polynomial and the divisor polynomial does not essentially match completely the p of x. There's a remainder. Okay, but you may have an exact division sometimes. So how do we apply that to neural net minimization, which is a big problem of great importance in machine learning? Because the modern neural nets, they have billions or trillions of parameters. How do you minimize them? Let's say let's take the example of a 2-layer and 1 output neural net. For every neural net node, we can formulate it as the difference of two max polynomials. So for each one of them, we find a divisor. by finding the most important vertices of the Newton polytope via the frequency of the of how frequently this node is visited and the weights of the network. Just an example. Here is for a single output neuron. This is the original polytope, and on the right you see the vertices kept of the polytope approximating that. This process actually it's a smoothing process. Let's say from the 8 vertices of the yellow polytope, we keep only the 4 blue. And this 4 blue is the final polytope. This idea can be extended. It has actually some interesting properties. It can be extended to multiple output networks by using the one versus all framework. The results produced are promising, very promising actually, but for simple data sets, large but simple data sets. I would prefer to actually detail more a more recent approach that we have developed for minimizing neural nets based on tropical geometry. This approach is entirely based on approximating the Newton polytope using Hausdorff distance. Here's the basic idea. Suppose we have, let's say, one hidden layer with ReLU activations for, let's say, for the ith hidden neuron. Its function is simply the max of a linear term, an affine term, and a zero. Okay, this is just a tropical polynomial. For the jth output now, we have a linear combination of these hidden neurons. Okay, these multiplication coefficients, we can separate them into positive and negative, and we can absorb them into the slope vectors A and the bias vectors of the affine terms. So we end up then, for every output neuron, we end up to represent it with a difference of 2 max plus polynomials, the P and the Q. And each one of them corresponds to a polytope. The hidden layers, the Newton polytope is just one line segment. So for every output then, we have polytopes. The one corresponding to the positive coefficients, it's the capital PJ, and the one with a negative coefficient, the QJ. And each one of them is a zonotope because it's a Minkowski sum of linear segments. The idea here is to approximate the extended Newton polytope with another Newton polytope so that it corresponds to a new network function, P tilde, that we want to be as close as possible to the original network function P of X. So one proposition here that is that comes in handy is the following. If P and P tilde are polynomials with coefficients from R max, and we consider they are Newton polytopes, then their max absolute difference over a ball is bounded by the Hausdorff distance between their polytopes. And we can extend that into the following theorem. If we have two neural networks with functions V and V tilde correspondingly, with output size M, and PJ and QJ are their corresponding polytopes for the positive and negative coefficient terms, then the neural network with function V is approximated by the neural network with function V tilde in a way so that their maximum, their N1 norm over a ball B is upper bounded by the sum of the Hausdorff distances between the positive polytopes and the house of distances of the negative polytopes over all output neurons. So then approximately equal polytopes produce approximately equivalent networks. We have recently this year actually improved this theoretical result by using for house of distance, not the house of distance only over the vertices of the Newton polytopes, but over the whole polytope. By doing this simple sort of improvement, the algorithms that I will be that I will show now right now, they have actually they have outperformed baseline and state-of-the-art approaches for compressing neural nets. So what are the algorithms? We have two algorithms. One of them is called the Zonotope K-means. We have a single output network here as an example. We have the two zonotopes, the green for the one sign, the other for the other sign. And then on the right, we have the approximated zonotopes, okay? And then we form a reduced neural net whose operation is very close to the original neural net. So that's the idea. So tropical geometry then becomes an extremely useful tool in understanding and designing this compressed neural net with very similar performance. What happens if we have multiple outputs? We developed a second algorithm called neural path, K-means. Before the compression before the approximation was done by taking, let's say, the vectors corresponding to the max plus functions for the positive and the negative terms, and we clustered these vectors, and we represented them with the centroids of K-means. That's the idea of compressing. Okay. Now, if we have multiple outputs, then as vectors, we don't just use the slope vectors and the bias of the output neurons. We also use the vectors for the weight vectors for the inputs. So we have an extended vector. We perform K-means on these neural paths. We call them neural paths. And this, the centroids of these K-means, it's a simple idea, but it works well. The centroids of this K-means provides us with the ultimate neurons to use. So we use only as neurons in the compressed network, the centroids of these K-means of the neural paths. The recent result, it's a very recent result here. Well, the recent result actually, the only difference between what I said and this result is instead of using for the K-means, instead of using the average of these vectors, we use the sum of the vectors. This simple idea, instead of the average using the sum, improves, actually reduces the house of distance. And this has a corresponding positive effect in the performance of the neural net. So we have several baseline approaches. What are the baseline approaches? The L1 structure, the random structure. Random means you throw away randomly some neurons. L1 means you throw away the neurons whose L1 weight norm is less than a threshold. The state-of-the-art approach is the thin net. Okay, and now we have actually applied this for deep neural nets, deep CNNs. Okay, for the NIST database and the fashion NIST database, and this tropical algorithm, the tropical neural net compression, which is our more recent algorithm, essentially outperforms both the baselines and the state-of-the-art. So we're actually quite happy for this performance. And we have not tried it on transformers, okay, only on CNNs. I think, the ideas, I think, need some time to mature. And in terms of neural network, we have also tried it on AlexNet, on VGG, as well as on LenNet. Okay.
Well, late, very late.
Okay, so I'm sorry. If you give me 3 minutes. Okay, the final class of machine learning systems we tried tropical geometry is regression. Everybody's familiar with least squares regression. Okay. In our case, for the tropical regression, we use the result of max plus algebra, where in solving max plus equations, there are two solutions that are of interest. The green one, the red one here, which I call the greatest lower estimate, which I explained before, comes from the adjunction. And if to this greatest lower estimate, you add half of the L infinity error, you produce the green solution, which is the minimum max absolute error estimate solution, unconstrained. So the red is constrained because it's always from below. The green is unconstrained. Okay, they both have linear complexity. And how do we optimally fit tropical lines to data? Okay, how do we fit tropical lines? It has two parameters, A and B. Well, we form a max plus system actually, and we solve this max plus system using either the green estimate or the red estimate. The new thing, which I'm very happy about it, is that the tropical regression then becomes essentially solving a max plus system of equations. And it has a closed solution, and the complexity is small. And if you have regression problems where your data actually bend, then this is the natural thing to do, to use a piecewise linear regression instead of a least squares linear regression. The same thing can be applied to lines that have that correspond to polynomials of higher degree. Again, a max plus system of equations that you solve. And you can also apply that to regression problems in two variables or more variables. Let's say, suppose you want to fit a tropical plane. You have three parameters, A, B, and C. Okay, again, you form a max plus system of equations, and the optimum solution is given by solving this max plus system of equations. You have two solutions, the red and the green. And you see some examples here. All this assumes, of course, that you know the degree of the polynomials that you're going to use. If you don't know the degree of the polynomials that you're going to use, then you're a little bit in the open. And one heuristic approach we have come up with is to do a k-means on the slope of the gradient of the data you're given, and use these centroids from k-means as the possible slopes only, and the number k of the centroids as the rank of the tropical function, and then solve again using this system of max plus equations. Here is some noisy paraboloid regressed using either a two-dimensional conic with 11 affine terms, or using the k-means 10, 25, 100. He found that a small number in the order of 20 or 30 in many dimensions is usually enough, but this is a heuristic. And due of lack of time, I cannot explain how one can improve on that by using sparse solutions of these max plus equations. So this, by using sparsity of the max plus solutions, one can come up actually with a smaller number of terms, as you see here in this example of regressing this noisy paraboloid. While keeping the number of while keeping the accuracy or the error close to the original. So, in conclusion, tropical geometry, I think, and its underlying max algebra, they provide useful and principled tools, and also they provide geometric intuition for analyzing several classes of neural networks with piecewise inactivation and neural networks with these max plus nodes like the morphological neural nets. They have similar performance and superior compression ability compared to their linear counterparts. Tropical regression is, is quite promising as a form of convex regression with piecewise linear functions. Neural network compression or minimization can be actually amplified by using ideas from tropical geometry. It's a hot subject in machine learning. So for future work, since we have many students in the audience, deeper networks, non-convex settings, more general functions, not just max plus, but max star, where this star can be an operation that distributes over max. For example, blue is the max plus, red is the max product, green is the max mean. Have a variety now of max algebra functions, unexplored yet, okay? And tropical approximation. Thank you for your attention.
Thank you, Petros, for this extensive overview of your very interesting contribution on the field. We are really running late, like very late. So maybe one question from the audience.
Santiago. Ay, papito, bendito sea Dios. Ahí están transmitiendo.
Could you please repeat? There are many people using.
Conferencista.
Sorry. You were talking about piecewise linear functions.
Yes.
And a lot of people are advocating for using smooth manifolds for describing those things. Could you advocate, as I understood, you could argue in terms of your models are sparse and maybe some computational efficiency. Could you advocate on a qualitative level for using the piecewise linear functions?
One motivation is the simplicity. As you mentioned, lower computational complexity, generality in the sense that it can approximate, a large variety of functions, and immediate connection with tropical geometry. For me, this is the greatest motivation because all of us understand the world more easily if we have a geometrical argument that helps us. And in the future, as I mentioned in the very last slide, this piecewise linear behavior can become smoother. It can become smoother in a variety of ways. One way is using this dequantization, replacing piecewise linear with this log sum exponentiation, okay? But computationally will be more complex. Linear functions, piecewise linear functions are computationally much less complex than exponentials. Another way is by using this max star algebra, which is completely unexplored yet. It's a new field, I think. Okay.
Toca buscar la grabación del día. Ahí está, hay que buscar.
That's Petros again. And
thank you. I'll be here all day. So.
yeah. So I think we can start.
Thank you. Thank you.
Maybe the people connected to Zoom. I think there's an open